Hello, everyone. We'll get started here in about a minute. All right, everybody, let's go ahead and get started. People are still coming in, but I don't want to punish people on time, so let's go ahead and get started. We are going to be talking today about the presentation installation guide for resistance grounding. It's the third installment of the our first webinar series. So we're going to go ahead and move forward with that. My name is Chris Small. I'm going to be giving the presentation today. Application engineer, regional sales manager. I've been doing this at Postcutter for about 12 years now. Graduated with my electrical engineering degree from Ohio State. So just in case that's important for some people. I know if you're a Michigan fan, I apologize, but just bear with me for a little bit here. So what are we reviewing today? Essentially, it's going to be fairly simple, straightforward. What are the benefits of resistance grounding? Usually in my other two presentations on this series, I would go over the kind of an in-depth analysis of what actually resistance grounding is. We're not really going to do that today. I don't think it's as important for this topic, but I do want people need to know who use this stuff, who install this stuff. A lot of times are the same people. So I want to make sure everybody understands the benefits of resistance grounding. Then we're going to talk about the installation of low resistance grounding, and then we're going to go into high resistance grounding. So let's go ahead and get started. Actually, before I get started, a caveat here. We are going to do a question and answer session at the end. If you have questions, please do not wait till the end to ask. There's like a questions tab. Feel free during, that way you won't forget what the question is. Go ahead and fill that out. There's one of my cohorts, Stu, me and him are going to go through all the questions at the end, and we'll have a question and answer session. So please go ahead and do that. So start off with resistance grounding. What is resistance grounding? It's essentially, think of a solid ground, a direct connection between neutral and ground, and put a resistor in series between those 2 points. That's what it is. So it's very similar to a solid ground system. So you just have to insert in series that resistance ground system, and you get a resistance ground. Okay. So what you're basically doing is you're impeding the amount of current that can flow through your ground. So when you have a ground fault, it lowers the amount of ground fault current you can have. So that is all that it is. It's from a schematic standpoint, it's fairly simple. So let's get into low resistance ground. So low resistance grounding is typically used at medium voltage systems. IEEE talks about how it gives you some examples of what it is. It talks about industrial application currents of between 100 and 400 amps. Those are typical values. When I'm talking about a resistor in terms of current, what I'm actually saying is amount of let through current. So if you have a certain resistor and it allows 400 amps of ground fault to flow, I would call that a 400 amp resistor. It's a lot easier than trying to figure out the math in your head and just go by the resistance. So that's what we're talking about. So just in case nobody knew that or somebody didn't know that, that's what it is. So it's typical for medium voltage. 25 amps is more of a mining application, typical. And then we're talking about 100 amps to 400 amps on the industrial side. And usually get higher than that on rare occasions on the industrial. And then some utility applications can go up higher than that. So typical ratings are 10 seconds. Actually, I should say, honestly, you can go extended ratings for this. So 10 seconds, 60 seconds, I would say is the most common, and 10 seconds by far being the most. But you can extend past 60 seconds. It's just pretty rare because at that point you're pretty close to continuous, and there's not that many applications that would utilize that. But it's possible, it can be done. Just want to let you know what's common. 3 major reasons for implementation. For equipment protection, think about a solid ground system where you're having potentially thousands of amps of fault current flowing. And change that to, let's say, 400 amps. So you have a much less amount of current flowing, therefore energy flowing, and therefore the amount of damage is much less as well. Essentially, energy times time, it's roughly equivalent to the damage you're going to receive. So obviously, if you lower that amount of energy way down, then you're going to be experiencing a lot less damage as well, relatively speaking. I said this especially for generators. In fact, IEEE recommends that a medium voltage generator should have impedance ground on the system, and a vast majority of those for industrial purposes are going to be resistors. So relay coordination, same idea. You're giving yourself a lot more time to coordinate. Once again, the amount of energy that you're exposing yourself to is much less. Therefore, your equipment's able to handle that for a longer duration. Now, when I say longer duration, I'm talking about typically milliseconds, but for a relay, that's a long period of time. So if I have a fault on a local motor, and I want to, obviously on a solid ground system, potentially having lots of current flowing, you may trip down instantaneously and potentially have a situation where your entire system is tripped. I've seen it happen. I probably get something like that happen at least once or twice a year, maybe a little more than that, in terms of installations where that has happened, and they usually change to a low resistance ground or high resistance ground system. So right through transient faults, that's another possibility. If you have these very short-lived faults that would trip on a solid ground system, you could actually ride through that with a much smaller current and be able to withstand that. So those are the reasons for implementation. In terms of application, it's very essentially any medium voltage application where you have a generator, or basically you have loads on the medium voltage. It's typically where you see it. You don't really see it almost ever on like transmission lines, or where there's very low probability of fault. You're usually seeing it in the industrial applications where it's where you do have those loads. So that's a synopsis for low resistance ground. Let's move on to high resistance ground. So you can actually use this low voltage and medium voltage. Historically speaking, we've been using resistance grounding, high resistance grounding for about 50 years, roughly. So historically speaking, traditionally you would use low voltage, high resistance ground, medium voltage, low resistance ground. You would trip on medium voltage. You might have some generator protection with the high resistance ground system, but for the most part, that was kind of the rule of thumb. I would say that has changed, or at least more people are aware that you don't have to do it that way. Essentially, safely, you can do it up to 5 kV. There's some debate whether or not you can go higher than that, but there is no debate about up to 5 kV. You can use high resistance ground. There are some design considerations. We may go over one or two today, but just know that you can use high resistance ground at that level. IEEE talks about the current range of a high resistance ground, is between 0 and 10 amps. Obviously, you can't have 0, but you're going to have somewhere between in that range. That institutes a high resistance ground. It's very good for process, for any kind of emergency generator or anything where you need your process to be maintained. That's why it's been used, like I said, for 50 years in oil and gas. Lots of food processing, any kind of process facility has been using this for a while, typically. Uh, Three major reasons: implementation, continuity of service, like I just said. The newer one I would say is arc flash mitigation. You have a situation where the amount of current flowing is very low at low voltage. Think about a 40 volt system at 277 volts. You have, you know, 5 amp system typically is kind of your default. For a high resistance ground system, that's, you know, a little over 1,000 watts of energy. You also have some voltage drop across that resistor, so you're going down fairly low voltage below really where you know, arc flash protection is needed. So the point is, IEEE states that on a ground fault, which is about 98% of all your faults, you have 0% chance of an arc event on a high resistance ground system. So just to review, low voltage, ground fault, 98% of the time, no chance of arc fault. And if, you know, I did a previous presentation on NEC, I think I covered where that NEC, or I should say IEEE says that. I think I covered that in that presentation. The last one is equipment protection. Essentially, same idea. I mean, if IEEE says it's safe to operate continuously, then your equipment is going to be protected. So you don't have to worry about that 5 amps flowing, damaging your equipment, assuming it's properly insulated, etc. So applications similar, heavy commercial industrial applications where, you know, process downtime is an issue, or you talk about safety or that mitigation, that, you know, the elimination of a vast majority. I've read, you know, papers that talked about 97%, somewhere in that range. So it's a large amount of mitigation there. Okay, so let's talk about the actual physical installation and start talking about installation itself. We'll start off with low resistance ground. Typical locations, usually we're talking about right next to the source. I mean, or as close as you can get. Essentially, any distance you give between the resistor and the XO, or the neutral of the source, you're going to be adding resistance, essentially. Now, it may not matter if it's 100 feet of cable, but we don't want it to be a large amount of distance away. And if you have to have it that way, it's not recommended, but you at the very least would have to consider the fact that you're actually adding resistance to the system, and your current values are actually going to be a little bit lower than you were anticipating. So you want to make sure you set your relays correctly. So anyway, it's very probable that you'd have a concrete pad next to the source. Seismic units, if you have that, I know a lot of people on the West Coast and some areas around the country are it's very popular to do seismic units, you know, shaker table type of units. Those need to be anchored to the ground, so you can't hang those up and expect to be seismic certified. Or you can't put it on a roof somewhere and expect it to be seismic certified. But also in or on a generator enclosure, typical to be, I've seen them mounted to the floor, I've seen them hung inside, I've seen them bolted to the roof. Just case in point, if anybody ever tries to do installation of one of these things, don't ever go on top of a generator enclosure roof when it's wet outside. I tried that, and it's an experience, let me tell you that. So another common way is on top of a transformer. Many of our customers, or I would say would-be customers, they order the NGRs, the low resistance ground, through a transformer manufacturer. The only thing I want to mention about that, obviously I'm a resistor manufacturer. I don't necessarily mind selling the transformer manufacturers, but I just want to make sure you're aware that a lot of my customers who I talk to directly are like, yeah, I think we're just going to order through the transformer manufacturer because we don't want to deal with the installation of the NGR. We want to put on top of the transformer. We don't want to deal with that installation. One thing I'll say about that is just make sure that's true. A lot of times the transformer with the NGR on top is too tall for shipment, too big for shipment, and they ship them separate anyway. So in my experience, you're paying roughly double the price. And if you're not getting them installed, you're having to do installation anyway. That's just food for thought, just to let you know. Just make sure that you're actually getting what you think you're getting. Or something like this may happen, right? So in terms of the clearances, so the low resistance ground systems usually has about 4 movable panels, one on each side. Usually those are, usually most panels are accessible. So you can usually only need 1 working clearance. So you should have 4 feet on that one side, and then the other 3 sides you should have a foot. So that's typically what it would be. I would be careful depending on what units you have. Some have like, you know, junction boxes, etc., where you may have an issue removing the panel with wires connected, etc. So just be strategic which panel you would use if you have only one. In terms of sizing, typically sizing is an interesting topic. I get a lot of people that comes to us and says, how do I size my low resistance ground system? It's hard for us to actually make that judgment because it's really based off of your relay system and your system in general, which we know nothing about. So usually I would say, typical sizes, I would give that recommendation. For 2.4 to 5 kV, we typically have 100 to 400 amps. A lot of times it's 200, like I mentioned. And then we get in the higher voltage range, it usually goes up a bit. I'd say 400 by far is the most common for those. Just consider the relay's ability to pick up 10% of the rated current. That's not always the case, but just understand that if you have a 400 amp resistor and your system, let's say, has 30, 40, 50 amps of continuous current or something higher, I would say higher than 10 amps typically, you'd want to look to see if you could pick that up with your system. Because if you have, let's say you have 50 amps flowing, you may or may eventually your resistor is going to fail essentially because you're higher than the rated current that it's able to handle. So if you have large amounts of continuous current, I would just consult with the manufacturer and say, look, we want the 400 amp resistor, we want it for 10 seconds, but we have this 20 amp, 40 amp, 50 amp, whatever it is, amount of current flowing, and we want to make sure to deal with that. I say I picked 10% because that's kind of a rule of thumb. I would say just to be safe, if you have more than, let's say, 10 amps of flow, you may want to check with the manufacturer and say, look, is your resistor able to handle this amount of continuous current? And if not, what would it take to do so? Because typically you're just going to go to a larger resistor and you can do that. But it's important to understand because if you had too much, you're going to have issues. One thing I want to note as well is resistor current must be greater than the capacitive charging current. This is not really an issue at a low resistance ground system. Although I have in a couple examples, I have seen that like in the last 12 years. But for the most part, we're talking capacitive charging current is less than 10 amps. So the system is probably going to be be able to withstand that. But just a rule of thumb, you want to specify it to make sure it's higher than that. I would say if you have a lot of snubbers, if you have a lot of things that actually contribute capacitance, and if you think you have a high level of capacitance, you may want to worry about it. And at high resistance ground, you almost always want to worry about it, but at low resistance ground, it's very rare. So in terms of NEC, obviously the NEC and installation go hand in hand because it's going to talk to you about what you can use and the sizing of cables and all that good stuff. And I've already done, a presentation on that. But just wanted to kind of give a synopsis of some references for you, just in case, because these are things you're going to need to know for installation. So size of ground and conductor, you have to worry about the current rating of the resistor, but you're basically going off of the table to the right. 250.66 talks about the grounding electrode. Then we have the equipment ground conductor sizing, and as well as the insulation and continuity. Insulation just essentially, what does your, for example, what does your XO cable need to be insulated for? You know, it needs to be fully insulated for the neutral current. And then the continuity is essentially, you know, you want to make sure that you're safely connecting. You don't want to have like equipment ground a part of your system ground, essentially. You don't want to make sure, if you have a system fault, you don't want that cabinet being energized. So that's basically what that section is about. So we're going to go ahead and do our first poll question, just to ask you guys a question, see what you guys think, get some results. We're going to go do that, and it's going to be just a few seconds here. We'll wait till everybody gets done and sees the results, and we'll move forward. It's our first intermission, I guess. It's going to be short, so don't go too far. We're going to probably another 15 seconds here. All right, so we'll go ahead and go. Just waiting for everybody. We're also checking to make sure you're in front of your computer screens. Just kidding. All right, so let's move on to the second section. In terms of cable entries, there's different ways to install the system, or based on your system and where the cables are incoming and what kind of cables you'd want to use. There's different ways to do it. I would say the top entry, it's very popular for situations where you have large cable coming through. There's not really going to be any room to bend that wire through. This may not be needed, as the ground wire, it may be smaller than you're thinking. Just go back to the table I showed before. But if you had a large cable and you didn't want to bend it through that conduit, you could attach it to the bushing on top of the unit, or whatever it may be. You may have wire coming out at a certain angle, and you just want to have a parallel resistor with that same angle, so you just have a straight cable coming through. There's all kinds of reasons why you'd use it, but just showing you how it would be done. A bottom entry is very popular as well. You would use a compression type lug, and you essentially bring it through that conduit, tie directly to the XO on the XO side, of the resistor, as well as with the ground wire to the ground side, obviously. And then bottom entry via CT. One thing I will mention though is that a lot of times we have customers that have issues with because the direct connect CTs, medium voltage CTs, have those horizontal bars that you have to connect to, and sometimes it's hard to come up through a conduit which you're at, which is basically perpendicular to that bar, and then come through and basically just bend that cable 90 degrees essentially at a very short span. So if you have that issue, I would say to use an L bracket bus bar. We can provide that. You'd have to order it, but that can be done. Otherwise, I would recommend using one. Don't use like an L bracket that you buy at a hardware store. Use a bus bar. So that's another option for you in terms of a low resistance ground, how to enter it. Those are the most common by far. In terms of maintenance, low resistance ground, so there's two different categories. We've got low resistance ground, high resistance ground. I will say that low resistance ground is much less complicated. I guess I should say it that way. It's really a couple connections. You have the incoming XO cable, you have the ground cable, you have potentially a couple CT secondary wires coming through. So it's not a complicated install in terms of wiring, but you should have some kind of a yearly or bi-yearly inspection. Also, look, for example, dust. Typically, just regular dust is not an issue for for resistance ground. Usually it would just burn off. I will say this, however, not all dust is created equal. I've been to pulp and paper installations where, you know, you open the cabinet and you see just piles of sawdust after, 6 months. That's not going to be a great thing. So if you had that scenario, you'd probably want to clean it out every third or fourth month. But you would know that. If you're at a pulp and paper plant and you have all the sawdust everywhere, I'm thinking a lot of the outside equipment is going to have an issue like that. We typically have a NEMA 3R enclosure, so if it's very fine dust like that, it's not going to catch everything. My point is that you know your system, you know your application. Maintain the units based off of that. I would assume it would mirror the other pieces of equipment in your system. So check for cracked insulators or bushings. That's always important. Like I said, yearly by yearly, it's typical. Another note, if you have parallel generators, make sure you're completely disconnecting the maintenance generator from the system. Typically, that's going to mean shutting down the whole system. If you have some disconnect means, which is shutting down the generator in the neutral, you can safely operate, but you need to make sure that neutral cable, even though it seems like nothing's going through it, potentially could have something if it's still connected. So you don't want to have that happen if your guys are working on it. So, and specifically talking about the resistor, we want to check the resistor element for continuity. Make sure that it's within 10%. Typically, it's the same thing for, after, how we test it at the factory. Just make sure, usually it's right on, but once again, it's acceptable within 10% of the tolerance. Check connections for tightness. Check wiring for heat damage. This is not typical if everything's hooked up correctly, but sometimes you may have a cable overhanging on the installation or something that's not done quite right. You want to make sure that doesn't happen. You want to vacuum dirt or debris, especially large amounts of dirt. Like I said before, there's scenarios where that could happen. And then, these things can get warm. Obviously, they don't last very long, but you may have some leftover heat that attracts an animal. That's happened before. Once again, these are typically NEMA 3R. We need to have air flow to actually cool off the resistor. So, there is possible for very small things to get in there. It's possible to also get screens, etc., but you have to specify that when you get the unit, because all that stuff impedes airflow. So we may need a bigger resistor if we're having screens, etc. So just a food for thought. So let's move on to physical installation of high resistance ground. This is more complicated. There's more steps to it, but I just want to go through typical locations: the concrete pad next to the source. Once again, all resistance ground, that's where you kind of want it. That's the most ideal situation. Seismic units must be anchored to the ground once again. It's very common to have a wall mount unit on either a transformer or somewhere on the wall where you have space. Usually it's where you have limited space, and you put the resistor up somewhere out of the way. Switch gear is very important, very common. I would say we sell a few hundred HRGs a year to switchgear vendors, manufacturers. So it's it's a large, actually maybe more than that actually, but it's several hundred a year. So you get the idea. HRG clearances, low voltage freestanding, 4-foot working clearance. In the front, that's all you need. Essentially, as long as we have that airflow that's able to get up through the bottom and out the front, we should be good. Medium voltage freestanding, 4-foot working clearance in the front, and then typically 1 foot on the sides. Our indoor enclosure has a little bit shorter. I think it's 6 inches, but you'll be safe with the 1 foot for sure. That's the outdoor enclosure. So in terms of sizing, I get a lot of questions about resistance grounding, high resistance grounding sizing. Okay, I had this size transformer. What size do I need? What about this size? You know, do I have to change based on the size of the transformer? The answer is no. In terms of actual electrical sizing, you know, current, you really only have to worry about a few things. Voltage being one of those things. We've talked about Ohm's law. It's one of the first things that I learned in my first class in electrical engineering. Essentially, you know, current and resistance are inversely proportional. So V equals IR. But if you change the voltage, let's say you have a 480 volt resistor that's made for 40 volts, you know, let's say at 5 amps, and you change it to a different voltage, you're going to change the amount of current that's flowing because the resistor is going to stay the same. The resistor value is going to stay the same. So you need to make sure that you're considering voltage when you're sizing a resistor, and also the capacitive charge and current. A high resistance ground, I mentioned before that typically these values are, you know, low, you know, under 10 amps, but our typical high resistance ground current is 5 amps. So it's possible to get higher than that, and that creates problems. And we're not going to go into all the details of why, and because it's probably a good at least 5 minutes, 10 minutes of conversation. But the point is that that's a design consideration, but that's all you have to really worry about for sizing in terms of current. And we typically have a tappable resistor. So we're talking 2 to 10 amps on low voltage, typically 5 to 12, or potentially 7 to 12, depending on which one you get on the medium voltage side. So you need to worry about this. I would say on the low voltage side, most likely you're not going to have issues with capacitive charging current because the cable is not large enough, and that's at lower voltage. So but that being said, I would recommend some flexibility there. That's why we have that tappable resistor. We also have a capacitive charge current measuring feature where you push a button, you know the charge current. So if you could push a button on startup and know your charge current and then set the tap accordingly, you're good to go. Otherwise, if you have a 5 amp resistor and that's all you have, and you figure out either through startup or through other means, oh, my charge current is a little bit higher than that, essentially you're out of luck. You need a new resistor because you cannot, that's a design requirement. You have to have the current flowing through resistor to be higher than that capacitive charging current. So we'll leave it at that. In terms of high resistance grounding, NEC, I just want to mention one thing. For medium voltage, I should say this. I mean, typically the high resistance ground current is going to be very low. Like I said, between 5 and 12 amps typically at the most. You're not going to have much current there. So you're not really going to need a large cable, but the minimum requirement is 8 gauge. So you're gonna have to use 8 gauge on high resistance ground systems. So you wouldn't typically use anything else besides that. But one thing I do want to mention on medium voltage installation, cable installation, you're going to need all your phase cables are going to have to be higher rated. So I think it gets missed sometimes. If you want to use a medium voltage high resistance ground system, you're going to need to potentially use elevated insulation of cable. And here's a chart that shows you per 311.6, a solid ground system or a low resistance ground system would use your standard cable. So if you had 5 kV system, you'd use 5 kV cable. And then if you wanted to use high resistance ground, but you wanted to clear the fault within an hour, you could use 133% rated cable. And then anything higher than that, you would need a fully continuous rated 173%. And like I said, so that adds a bit of cost. Usually people who are using medium voltage high resistance ground are doing so for continuity of service, and it's worth it for them. So whereas at low voltage you would be using it for that arc flash mitigation, that safety aspect of it. It's more so just the continuity of service at medium voltage, because you could potentially it's not, there's still a lot of energy at medium voltage where, so that's the main reason. So neutral connections, we have a a 5-pole disconnect on our unit. Now, I will say that we do have an option to have a continuous neutral, but typically speaking, we have a 5-pole disconnect switch. Your 3-phase cables, you actually have 2 neutrals. We ask that you parallel 2 cables from the XO of either your transformer or your generator. One thing I will mention is a lot of people say, well, either I've seen it in the field happen, or I've seen people ask the question, why can't we just jumper this, Chris? So I have this XO coming in, my 8 gauge cable coming in here. Why can't I just jumper from this neutral over to here and just monitor that way? And the answer is you can. So this sensing resistor neutral right here, or this input right here, is actually used for a current for a voltage loop here to monitor this neutral. So if there's something that goes wrong with this neutral, if it opens up, we're monitoring that neutral. And so if you have it like this, you're going to be fine, except for one thing. Your monitoring starts here. This is where your loop starts, and it goes here. So this is what you're monitoring. Everything besides this XO cable right here. So if you want to monitor the full neutral cable from the transformer all the way to the resistor to ground, then you're going to want to have these 2 connections here, these 2 right here, and go without. So this is the way you want to do it if you want the full range of visibility. But once again, you can do it this way. Just know what you're giving up. So in terms of one thing I did want to mention on our units is that a lot of times I'll see in the field Ethernet connections going into the wrong port. You can see here, although right here is where the Ethernet connection would be, but this is where you have your 2 ports coming in. So you have your RS-45 port, you have your Ethernet port. Those are where you make your connections. I've seen a lot of people put their Ethernet cable into this auxiliary port, and that's not going to work. So that's the other side. So you can see there's the front of the screen. When you open the door, this is what you're going to see facing you. This right here. This is obviously on the other side, but this is where you want your Ethernet connectivity. And then if you have RS-45, obviously you want to hear as well. In terms of other things to note, a lot of times during installation of a high resistance ground system, I mean, we're not going to go into the great detail. There's programming, there's different things. It's not exhaustive, but it's more than we have today. My point is here is general installation instructions, how to do it, wiring, etc. But just some notes on this part of it. You have an SD card that stores backup firmware, stores data tables, etc. This is what you're going to use if you need to upgrade firmware, etc. But this is where the location is. You actually push your thumb in there, it pops out, and you can change firmware, you can change data tables, you can download data tables, etc. off that SD card. So that's all about that. Essentially, there's a system directory where you'd actually, one way to do the firmware upgrade is we actually would email you the system file, the firmware file. You would replace it into the system directory on the card. So that's how you do the micro SD. In terms of settings on the resistor taps, this is how it looks. You have your green wire, which is the resistance value, and this is the tap that you'd want to change. You have several taps, 7 taps total, and then your numbers correspond to the amount of current that's flowing, that let through current. So your standard connection is your 5 amp connection, and then your standard pulse, which is the white wire, is your 10 amp connection. So most of the time you're going to be keeping it like this. For some reason, if you want to move this down and you know that the charge current is low enough, you can do that. Go ahead. Make sure that the pulse stays to the right or stays higher than the resistor value, because if you cross these wires, you're basically going to lose your pulse functionality. It does not work that way. So just keep that as a note. I would say the vast majority of everyone who's using these systems would not ever change these wires. But you can see here how it works. Basically have your pulse contactor. and you're essentially shorting out a portion of your resistor and changing the ground fault current, essentially what you're doing on a pulse. You're pulsing back and forth. That's how that works. So let's move on to our second poll question. It's going to be our last poll question. Some of you may be relieved, but the point is that please just take a few seconds just to answer that, and we can move on to the last portion of our series, of our presentation. Okay. Let's go ahead and move on. All right, so kind of go into troubleshooting of the unit. Essentially, you have this is your main interface. This is your controls in the back of your. If you open the door, this is what you see. You want to, I mentioned the SD card, you want to check for the latest firmware version. You want to make sure that it's there. I always mention that because if for some reason there's an issue with the firmware, which most of the newer firmware would not have, but just, if you have a really old version of firmware, regardless of what firmware you have, my thought or our thought is really, if you have the latest firmware, you're getting rid of that possibility. So just always have the latest firmware. That way we don't have to worry about it, and we don't have to worry about checking the firmware for at later times. Check to make sure all the customer connections are correct. There's not that many. There's I was mentioning the 5-pole disconnect. You have your 3-phase cables, like I mentioned, your 2 neutral cables, and you have a ground bus coming in to probably, I'm guessing it's lower down here on this is a freestanding, so it's down here by the resistor. The point is that you want to make sure all those connections are correct. And then, a lot of times we get calls. It's, look, I'm not getting this kind of functionality out of the unit. What's going on? The first thing we ask people is, okay, did you disable the password? It sounds really simple, but you don't actually have a full functionality of the system until you do that. So that's the first thing you should check prior to troubleshooting. I will say we have 2 different diagrams I want to show you. This is I would call it a point-to-point wiring diagram. Very good for checking wires. Very good, just make sure all the wires are in the right place, and usually it corresponds to the label. Essentially, it tells you where the wire is going. So if you see here the wire coming out of your terminal block, it's going to appear. This wire is going to your CPT, so you know where it's going. So you kind of can check, and that's how you can check point to point fairly simply. If you're trying to troubleshoot, though, I would say I would use this instead. This gives you a more functional idea of how the system works. If you're trying to figure out how the system works, you definitely use this diagram. It gives you an idea of how, what relays make what work, etc. So I'm not going to go through specific, many more specifics than that, because it's going to be for a tech, and usually he knows a lot about that. But just know that these are the resources. You don't want to. I would not recommend using if you're trying to troubleshoot and figure out what's going wrong with the system. Besides wiring, I would use this one. So a couple different problems. What does it look like? The HRG does not energize. There's, there obviously could be several situations. Do you have all your phase cables in? Do you have all your customer connections? That's always obviously the first thing I would look at. Do you have fuses that are blown? You can look for defective switches. I would say I've seen several times where you have, a connection. In fact, let me go back and show you real quick. Oops. Oh, I can't see those here. All right. Well, there's a terminal strip on the top of the controller. That's a Phoenix terminal strip, and essentially you are sometimes that can be disconnected, or something. Well, typically what happens is you have somebody who opens it up, who disconnects it for some reason, and then tries to put it back in, doesn't push it in all the way. That's another thing you need to look at. Once again, defective switch, that happens rarely, but it's possible. Defective power supply, it's also possible. Fuses, I would say, the most common thing. Look for that adapter switch as well. Just something to think about. That terminal strip is loose. Make sure that's pushed in. Otherwise, it's possible you have a bad controller. There's a few things. These are probably more common, but you can check those circuits with a multimeter. Test button does not operate properly. You push the button in, you're expecting a certain value. Typically, if you push the test button in, you're looking for, at a low voltage unit, you're looking at roughly 135 volts, roughly around there, between 125 and 135, roughly 2.5 amps. There's things that could happen. Essentially, you can tell a lot by what values you get from the test resistor. So you don't want to ignore that. I've had several situations where the customer calls us in after a startup because whoever did the startup kind of missed a nuance in the test resistance. They got values, but they were a little bit off, and it probably would have told us something, but they missed it. So the point is that you want to pay attention to that. What could happen to it? For example, if you have a solid connection on your system, on your neutral, you're essentially not solidly grounded. You won't be getting much out of your test resistor. So you push the button, you get a click, you get interaction from the circuit, but you don't see any voltage or current flowing. One possibility for sure is you have a solid ground. The next thing I would do after that is I would take a multimeter, actually measure an exo to ground resistance measurement, and see if that's solid grounded. I mean, it's as simple as that. I would say a lot of the times it could be. I've seen it several times. I've done, I don't know how many starts I've done. I've done several hundred units, and I've seen that a lot. So the point is that that's definitely a possibility. You could have incorrect voltage on the test circuit. Open resistor, it's common. You usually would have an alarm for that, but all these things could happen. So you want to make sure that you're paying attention to the test button when it does not operate properly. In terms of maintenance on the high resistance ground system, you want to, once again, same as before. Now there's a lot more controls in this unit. If you're going to do it once a year, that's probably okay, depending on the environment you're in. But once again, if it's dusty, you may want to do it more because you don't want a lot of dust in the control cabinet. But usually, I would say from experience, under normal conditions, once a year is fine. Check your wiring connection once again. You always want to check the resistance. I would say most of the time you're gonna have issues on startup. Somebody was a bad customer connection, or there was there's obviously we could make a mistake. I'll be honest, it's not very common, but with wiring, but we could do that. Or if there was an OEM that was installing it, they could have installed it incorrectly. So those things, you really should make that part of your startup as well as your maintenance. Once again, if somebody accidentally puts a ground somewhere, let's say they're installing a isolation transformer and they accidentally ground the primary, that's going to solid ground your system. So if you do a resistance check on that in that HRG cabinet between XO and ground and find out that it's 0, something happened. You would need to address it right away. You're solidly grounded. Otherwise, it should be, if it's 5 amp tap, you should be at 55.4 ohms. So that would be a good test. But it's always a good thing to know. It'll tell you when things are going wrong if you don't have that value. You want to complete a test function on the unit. Make sure, like I had mentioned before, you're getting expected values. If it's between 125 and 135 and roughly 2.5 amps, then you should be good to go. Otherwise, there could be an issue. So you want to double check that. You can always call us to ask for help if you're not sure about if it's performing correctly. Check fuses. That's kind of an obvious one. Do with all your stuff. Check the charge current. This should not ever change unless you add stuff to your system. But once again, that happens. So if you are, I would just always check it if you're adding stuff to your system. But if that didn't happen, just make sure it's part of your maintenance schedule, and that make sure that the charge current is low enough. If you can perform a lamp test, make sure your lights are working. Just double check all your alarm value settings. Make sure that you are operating at the same alarms. You want to make sure that if you have a 5 amp tap, that you have somewhere at 5 amps or below to the alarm. It's kind of obvious stuff, but people can get in there. It's password protected, so not everybody can get in there, but it's happened before where people have changed the values and you're not getting alarms because it's programmed incorrectly. So just make sure all the stuff's right. One thing I do want to mention is your PLC battery. There is an internal battery in the PLC that lasts about 7 years. It needs to be replaced. So if you have a maintenance program that's more long term, I would say every 5 years to be safe. That way, it's usually a 5-minute operation. Take the lid off the PLC. You have to obviously discharge the system. Take the PLC out and unscrew the lid off of it. It's not a very complicated operation. We have a literature on it if you need to have it, but the point is that you would need to replace that. It needs to be part of your maintenance profile. Startup considerations. Who is qualified? I will mention that we do startup. We don't openly, promote it, but we do just as a service. Is it always necessary to have us do it? No. I will say this, there's a big caveat here. It's very simple when everything's hooked up right, when all the wiring's done correctly. The startup can take 15, 20 minutes and you're done. And it's like, wow, that was really simple. But if something's wrong, you have a bad wire, you have a bad component, something's wrong with your system, let's say you're solidly grounded, it can get a lot more difficult. So keep that in mind when you're looking to see who's going to do the startup. It's like I said before, it's really easy until it's not. Once you have a problem, it can get kind of difficult, but we can definitely help you out with that. I will say, look, if you don't have that in your budget, that is fine. I would say if you run across problems, once again, it should be fairly simple, but if you run across problems, you can always call us. We have people that help with troubleshoot, help with talking to you over the phone. It's not always simple to do that over the phone, but we can definitely help. We know what we do hundreds and thousands of units in terms of over the years, so we have some experience and to know what could be causing your issues. I will say, a lot of times it's a system issue. It doesn't have to be. It could be a resistor issue, but I guess my point is, don't assume that because you're getting an alarm on the HRG that there's a problem with the HRG. The good news about the high resistance ground system is it can actually diagnose things with your system. So it can definitely be an issue with the HRG, but it can also be, for example, solid ground system or something like that, or if you have an open neutral, etc. So in conclusion, I just want to talk briefly about the grounding. Essentially, you have grounding is very important. It's usually kind of left to the end in terms of specifically how they're going to do it, but it's for a safety perspective, for an operation perspective, it's crucially important. So you want to make sure that you are doing it right. Not only are you specifying it right and engineering it correctly, but you're also installing it correctly. Once again, LRG is typically much simpler than HRG for installation. This is true. Not saying that it's less important. It's not. It's just that most people who deal in electrical situations, contractors, etc., they can handle hooking up an EXO from the transformer to the resistor and then from resistor to ground. So I'm not saying you can't get help from a low resistance ground system startup, but more likely you would probably need help on a high resistance ground startup if you need any at all. And then proper startup and maintenance are essential. So obviously you want to make sure you're maintaining the equipment just like anything else. You want to make sure it's maintained properly. But because it's the first line defense you have on your grounding system, you want to make sure it's done right. So that's how it works. So hopefully you heeded my advice and you were asking questions during the presentation. So we're going to go ahead now to me and Stu are going to talk about maybe some questions that came up and go from there. So Stu, do you have any questions?
A couple of quick things on the poll questions. 85% of respondents have not had problems when doing HRG installations, and 50% of respondents actually use a contractor to do their startup. 10% of people don't do startup at all. The first question actually came from a couple of people. It came from Nadeem and Joseph. How do you perform a charging current measurement, and/or are there rules of thumb?
Okay, so I'm trying to think of the question. So how we do our system, I mean, it depends on how you want what you're talking about. If you're talking about our units, our system charging current is basically done by a push of a button. We do it internally. We essentially take, to make a very simple version of it, is we're measuring, resistor current. We're measuring values across both the resistor and the test resistor, and we're basically taking what's left over and we're saying this is what the charge current is. So we have a measurement. I don't have the formula, but basically you have a total overall system current and you have a resistor current, and the difference is the charge current. As far as the process to do it without our unit, essentially you have to, I would recommend through a test resistor, creating a fault. Essentially that's what we do. We do it inside our system, but that's what you'd have to do if you were doing it without our system. So you'd have some kind of test procedure. If you're interested in knowing exactly what that is, we can give you that literature, but the point is that essentially you're creating a fault, a controlled fault through a test resistor, and you're looking to measure how much current is left over from the resistor, so that you have your leftover charge current value.
I was just going to throw out, alternately, you could sum up all your cable length, all the associated capacitance per foot, all the insulation in your motors, and manually add it together if you're so inclined.
Yeah, maybe I misunderstood the question. Yeah, that's how you could definitely calculate it. In fact, I would say if you are already low voltage system, I would recommend you don't have to do a calculation. I would say typically you would be fine. You might want to, like I said, add some flexibility with a tappable resistor. A capacitive charge current measurement wouldn't be bad to go along with that as startup. If you're doing a medium voltage system, I think you have to do a calculation before you even start, because you don't know if you can do it or not. Medium voltage typically, you have higher capacitive charge current values. Essentially, the idea is if the current flowing through your resistor is higher than the current flowing through the capacitive charging current, you're not going to be able to use resistance ground. Or in other words, if your system capacitance is too high, your charge current's too high, you cannot use resistance ground. So, or at least high resistance ground. So you definitely want to measure that calculate that at medium voltage. I thought you said measure, so sorry about that, but go ahead.
There was what amounted to a follow-up question from Ethan. Are there any considerations that have to be made using HRG on a low voltage system if you also have power factor correction capacitors?
Yeah, so essentially, depending on how you wire those up, you are going to be having extra capacitance on your system. So I would say the short answer to that is, can you hook it up delta or phase? Can you hook it up line to line versus line and neutral? If the answer is yes, that's the best way to go. Otherwise, you're just going to have to deal with that added capacitance and make sure that it's still low enough to be able to use high resistance ground.
One question came in from Lawrence. Enclosure types for high resistance grounding. Are they NEMA 4, 4X, or are they 3R?
So, yeah, so I didn't mention enclosures too much because it's, I mean, it's more of a specification than it is installation. But you typically resistors are going to be NEMA 3R. We have certain cabinets that have NEMA 4X rated components and controls, but the resistor itself is typically going to be NEMA 3R. It's a convection cooled resistor. Is it possible to do a NEMA 4 resistor? Yes, but you're going to need some kind of a forced air situation where it gets more complicated, more potential failure issues. So I guess the easy answer is almost always you're going to have NEMA 3R resistor, but you can definitely get the controls in 4X to make sure that there's no issues with the controls.
Question came through from Dan. You gave NGR clearances of 4 foot or 1 foot. Is that post Glover or is that an NEC requirement? And what would the NEC requirement be?
Well, I do know the working clearance is, I honestly don't remember where it's at, but it's probably an NEC. But it definitely is a requirement that you need. So you're going to need that 4 foot. In terms of the other foot, that is, I mean, it's going to be typical. So you have to remember that most manufacturers now, it depends, right? A lot of manufacturers do it the same way in terms of low resistance ground. You're going to be doing very similar pieces of equipment, so you're probably going to be seeing the same types of clearances. But technically speaking, I can't tell you for sure. Obviously, there could be competitors of ours that use a different variation. But I will say this: I mean, you're going to have the same as long as they meet the IEEE requirements. You're going to be having the similar, temperatures. So it's going to be. I guess the easy answer is those are post-Glover requirements besides the working clearance, but you should see it fairly similar across the board.
So in other words, the 4 foot is more of a working clearance to be able to have a person get in there with hand tools and do work. The 1 foot clearance is more for heat exhaust and air intake to be able to keep the resistor properly cooled under operation.
That's a very good way to put it, Stu. Yes.
Question came in from Mike. What would be the difference between using a resistor and an air core reactor as a grounding point?
Well, I will say this. You're going to have it's two different types of impedance grounding. I will say, based off of research that I've done and IEEE papers, et cetera, for industrial applications, 90 to 95% of the time you're going to see a resistor. I'll give you a short answer. Actually, to be honest with you, we're going to be going over this in a couple months and get into detail about this question. But essentially, you need a much higher ground fault current in a reactor, a much higher. Usually it's typically 65%, which I would say, I think technically 20 to 65% of your three-phase fault current needs to be the ground fault current of your reactor. So you're going to have much higher ground fault current. So there's issues with that potentially. It's much more common at higher voltages, like 35 kV and above. But for industrial applications, it's much more likely to use a resistor. Other than that, I mean, like I said, if you're interested in that topic, a couple months from now, we're going to have a paper on that exact topic. So I would say wait for that. But there's a lot of differences, and then I'll go into detail about all the differences. But once again, just to drive the point home, white paper, IEEE white paper, 95% of industrial applications are typically resistors.
And in my best effort to keep us on time and get this through in the allotted slot we had, can you install, and this is from Johan, can you use HRG or LRG in classified areas? So class 1, div 2, type environments?
Yeah, for sure. The answer is yes, but I guess yes, but right. So you're going to have, depending on the environment that you have ignition temperature requirements that you need to meet. So you need to make sure the resistor is designed. Basically, I would say, typically speaking, you're going to have a custom resistor. We may have done it before. We probably have done it before, but it's going to be a larger resistor that meets that threshold, or goes below that threshold, I should say, so that you don't have any ignition issues. So you're going to have the short of it is you're going to have a much larger resistor, but you can definitely do it. You can definitely put it in a class 1 to 2 environment. You just need to know that temperature requirement and make sure that the delta T of that resistor plus ambient is going to be below that value. So once again, the standard temperature rise is 385 degrees C on a high resistance ground system. You're going to be doing much lower than that, usually half or less. So once again, we're increasing the size of the resistor. So as long as you understand that, we can definitely do one, but you're going to be having a bigger resistor. Well, so I think, guys, that is all. We are going to have these as far as I know, for the near future, going to be having these monthly, and we'll be coming out with a new series here shortly. So you guys know, I gave away one of the topics, obviously resistance versus reactive grounding, but otherwise, stay tuned for that announcement for all our next 3 in our next series. So I really appreciate you guys' time. Hopefully you guys learned something, and it was worth your time. But until next time, appreciate it. Thanks, guys. Take care.